This presentation will be on some of the work that came out of my PhD. Basically in investigating eddy activity using FASOM, we came up with a fully eddy resolving in the Southern Ocean configuration of FASOM, so a regionally focused mesh, ran some simulations with that, and then applied it to the high southern latitudes. So to begin with, I'll go over the motivation for looking into eddy activity in the high southern latitudes. It's often omitted in climate simulations and from observational studies, which I'll get into a bit in a moment. And so I want to not only look at the effects of eddy activity in the high latitudes, but how those effects can relate to the climate and climate change. So just to go over a few impacts, the first, this will be one of the regions that inputs the most meltwater into the oceans as things warm up. And there's evidence actually that eddy activity is one of the primary drivers of warm lower latitude waters across the Antarctic shelf break and towards the ice shelves and marine terminating glaciers and so on. As well, this is one of the major sea ice regions of the world, one of the two, and so it has a outsized impact on Earth's albedo, and as well on the regional circulation due to the freshwater flux that it produces. And again, there's evidence that eddy activity can influence the sort of seasonal growth and melt cycles of sea ice, such as by disturbing the sort of insulating meltwater layers that can occur beneath sea ice as it begins to melt. And finally, the high southern latitudes contain the major production regions for Antarctic bottom water, which is this sort of abyssal layer of water that fills the global oceans. And there's evidence that eddy activity is one of the key components of producing that bottom water and, as a result, contributing to overturning circulation, such as through the input of different water masses into the high latitudes, sort of beginning this process, and as well modifying the water as it sort of continues through that cycle. I'll touch on these a little bit more later, but overall, I think it's just worth looking into the region because there hasn't been a lot of research on it up to this point. So in trying to set out a baseline of what we do know about eddy activity in the region, I have this figure here from one of the great papers characterizing Southern Ocean eddy activity from Ivy Frenger. And in this paper, they use observations, so mainly the altimetry record, to try to characterize eddy activity in the region. And of course, the information just stops at about 65 degrees south, and that's because that's where the seasonal sea ice cover really breaks down the altimetry data set. So if you can't see the ocean surface from above, then you don't have quality satellite data. More recently, there have been attempts to extend the altimetry data set down to the seasonally ice-covered region using sea ice leads, but the problem then becomes the resolution of the data product. So this has a resolution of about 25 kilometers, and the data that data product is sort of interpolated from can be even more sparse, given that it comes from sea ice leads. And so there was this attempt by Alger et al. To do some eddy tracking in the region, but frankly, given the Rossby radius in the region, we shouldn't expect this data product to be able to capture eddy activity there, or at least much of the eddy activity there. And so the natural question for this group then, I guess, will be, okay, well, can we just use model data to look into this region? And the problem is, again, the small eddy size. So with a Rossby radius of less than 10 kilometers in much of the region, it's very computationally expensive to resolve the eddies here. And as a result, high latitude eddy activity is missing from virtually all major simulations of climate change, such as all the CMIP simulations, omit these processes. So I think it could be something really interesting to look into. And so part of my PhD was coming up with a configuration of FESOM that was fully eddy resolving in the Southern Ocean. So the grid that we came up with to do this, we refer to as SO3. So in the Southern Ocean, SO, it is finer than 3 kilometers. We get up to about 2.55 kilometers resolution. And in the rest of the globe, it's about 25 kilometers. So still something that would be high resolution in CMIP6, for example. But as you might expect, this is then a pretty heavy mesh. So there's 11 million surface nodes. We produced about 1 terabyte of data per variable per year of 3D daily data stored on nodes. And the throughput was highly IO dependent, so this may not be so relevant to others, but I got about 2/3 of the simulated year per day. But we were pretty much eddy resolving right up to the Antarctic continent, and in some places eddy permitting, where the water column starts to get shallower, and then some places as well not even eddy permitting, but still quite good, and still very state-of-the-art, I would say. But given that this was part of my PhD and I didn't have all the resources to throw at it, I had to go about reducing the computational cost of working with this mesh. And so the first thing that I had to do was, rather than run it as a coupled simulation, to run it as a standalone ocean. And so I used the atmospheric data that was produced by AVI for CMIP6, as well as the sort of medium resolution mesh that was used by AVI-CM and CMIP6 to begin with. And so this sort of stemmed from a previous work that I actually gave a previous science hour for EERIE, which you may recall, which is why it's a little bit stemming from the CMIP6 data. But anyway, it's also a good atmospheric data set to simulate climate change from 1850 to 2100. And then I use this medium resolution mesh as a sort of spin up and transient simulation. But then I took the ocean conditions, the ocean data from that medium resolution run, and used it to initialize the high resolution setup. So I ran 3 different time slices there at different points during the progression of climate change. I discarded the first year as a true spin up. And so then what I was left with were 3 time slice simulations with a fully eddy resolving Southern Ocean at different points during the progression of climate change. So I did publish a paper evaluating this earlier in the year, and I won't really go into the details, but mainly what we did was compare to the observational data set and to the projected impacts of climate change that we got from our CMIP6 simulations. The only thing that I do want to point out from this paper is that we found good agreement with the CMIP6 simulations, so good agreement between the high resolution projections and the ensemble of projections that we had from CMIP6. But we were able to basically evaluate that using the ensemble. So using the ensemble as a measure of the climate change signal to the noise of natural variability. And one thing that we found is that without that ensemble to compare things to, the changes that we see after 1 degree of warming would be difficult to distinguish from natural variability, whereas after 4 degrees of warming, they became quite clear. And so for this analysis, for this presentation, I'm going to limit the analysis to the changes, or at least the assessment of the impacts of climate change, to what we see between the sort of historical 1950s, almost pre-industrial period, and the end of the century prolonged warming period under emission scenario SSP 370. So the last thing that I'll say before we get into the results is just some of the analysis that I've done, because it's going to come up in the next slides. So basically, I've done some eddy tracking. I use the Okubo-Weiss parameter for this. So it's a little bit more simplistic than other methods, but it allowed us to do some things like look at sort of 3D structures, which sea surface height-based methods could not. And so from that, I can get some sort of Lagrangian data to really characterize the eddy activity that we see. Then we have more direct model output and what we can calculate from it. And finally, I'm going to try to relate all of the characteristics, both historically and in the context of climate change, to larger regional circulation features that we have a much better understanding of. So to get to the results, the first thing that I'll try to do is characterize the historic mesoscale structure, because as I pointed out a little bit earlier, this is a region where we don't even really have a good assessment of how things stand today or historically. So here I have the tracked eddy presence in red and the propagation directions overlaid in black. And these distances are exaggerated by a factor of 4 for visibility, just so you know. And the first circulation feature that I'll start with, even though this is a bit not the focus of the study, is the ACC. So this is fairly well understood, but it's around the periphery of our study region. So we can see its effects. Basically, we have this very energetic eastward propagating current. I won't need to tell you guys that. And we can match that up very nicely with the eastward propagating eddies around the periphery of the study region with high eddy kinetic energy, given that it's a very high energy circulation feature. And then we can also look at the characteristics of the eddies that we see and say, okay, where we have these large eddies, I mean, given that it's a more lower latitude feature with on a large scale. So where we have these large eddies, high eddy kinetic energy, and an eastward propagation, we can pretty confidently associate this with the ACC. To move a little bit more poleward into what we sort of aim to look at in the study, we then get the Antarctic slope current, which is a still energetic, but less energetic than the ACC, but relative to its surroundings, quite energetic current that propagates, flows westward around the Antarctic continent. And then referring to our eddy activity, we can see, okay, we have a little bit of this in-between region, and then we have nicely westward propagating eddies that we can pretty confidently associate with the Antarctic slope current. Pretty basic stuff. It also checks out very well with what we already know about eddy activity. So where we have bathymetric features steering the flow of the large-scale currents, we tend to get higher eddy activity. That matches up pretty well with what we see in the Antarctic circumpolar current from more well-known research. And then the final circulation feature that I go over is the gyres, so the Ross and Weddell gyres. And I'll point out that these are much less energetic features. So we don't expect to have the barotropic eddy generation that we probably get from the two currents. But what we do see is that where we have the sort of recirculation of waters from the lower latitudes into the high latitudes through this gyre circulation, we can get eddy activity from the baroclinic instabilities that the water of different density, different properties introduces. So it's a little bit easier to see with the Ross gyre just because of where the region is cut off, but we do have this, relative to its surroundings, higher eddy activity with this sort of southward propagation. And the last thing that I want to go over in terms of the historic structure is the sort of relationship between the background flow and the propagation and lifespan of eddies. And again, this isn't super groundbreaking stuff, but basically we have this inverse relationship between the speed of the propagation speed of the eddies, which is related to the speed of the background circulation. So where we have the Antarctic circumpolar current and the Antarctic slope current flowing pretty quickly and pretty energetically, we have high propagation speeds, reflecting that eddy movement is primarily coming from the background flow rather than their own propagation. But then where we have that, we tend to get the mean flow sort of reincorporating the eddies, so reabsorbing them. And so we have very short lifespans. Whereas when eddies sort of break away from that energetic background flow, they can have much longer lifespans in these gyre interiors, for example. Now, you might be saying, okay, the relationship looks pretty clear from the figure, but what's the actual relevance of this? And I think this is one of the really interesting results in that we essentially have two different ways in which eddies are going to be causing mixing and breaking down isopycnals. This is again from a Ivy Frenzer paper. So we have stirring, where the circular movement of the eddy activity can sort of mix tracers, and we also have trapping, where the propagation from one place to another can break down isopycnals. And so we can see that there's perhaps two distinct ways in which eddy activity is affecting the different regions within the larger study region. That I think will come up a little bit later, but Before that, let's look at the projected impacts of climate change. So here I have the change in tracked eddy presence between the two periods. You can tell that these changes are pretty complex and pretty distinct in different regions, and I think that makes sense given that this is a very complex region in terms of the circulation, but I will try to explain at least some of the changes that we see here. Beginning again with the ACC, so sort of what we've already, what's already been studied quite a bit and what we understand quite well. We can look at the same tendencies that we use to associate eddy activity with the ACC, such as the eastward propagation, the high energy, and the large eddy size. And we can look at those changes to tell us what the change in eddy presence is caused by. And so it's pretty, I think, pretty clear and pretty well understood already that we have a sort of ACC intrusion where the southward shift of southern hemisphere westerlies is going to push that south. And so we get eddy activity from the ACC reaching further into the high latitudes. Before I get into, so to break from the sort of progression of features that I went over first, I'm going to talk about the Weddell gyre because I think this actually has a lot to do with the other changes that I want to talk about. So here I have a illustration of the Weddell gyre circulation. It's actually a little bit more complex than you might see just from plots of something like stream function. This is from primarily in situ observations from the Polarstern. And so I want to point out two features in particular. The first is this cold regime where you have water masses from the interior of the Weddell gyre recirculating with that gyre in the interior. And so they're already cold and tend to be salty from sort of just existing in the gyre interior already, and they can recirculate. And then on the other hand, you have these warm inflow regions where you have ACC waters, so warm deep water flowing poleward and entering the high latitudes and the gyre circulation. And from this paper, where they directly observed this recirculation and this inflow in situ, they basically identified two cores of inflow into the Weddell gyre. The first is the C1, as they mark it here, which they primarily associate with eddy activity breaking off of the Antarctic circumpolar current and entering the Weddell gyre. And then the second core is primarily associated with the Antarctic slope current. So ACC waters can flow further downstream along the ACC and reach the higher latitudes upstream of the Antarctic slope current, and then you get a second core of inflow. But to focus on the first core, which they relate to eddy activity primarily, so eddies breaking off of the ACC, we can see that historically we have relatively heightened eddy activity breaking off of this region. And then in the context of climate change, we see that substantially decline. And so we know that the flow of the ACC is shifting primarily due to westerlies, is the theory. But so one of the results of that may be that we're sort of losing or at least seeing a reduction in this core one of eddy activity forming an input of lower latitude water into the Weddell gyre. So that's a long explanation to say, okay, well, this might be a shift in the ACC, removing one of these inflow regions. But I think it's really interesting to ask ourselves, okay, what might the effect of that be? And before I get to that, so I brought up the Antarctic bottom water production in the beginning of this as one of our motivations for actually looking at the region. And as it turns out, if you're not a polar oceanographer like I'm not, as it turns out, this warm inflow actually represents one of the precursors to Antarctic bottom water. So this is a crucial step in the production of Antarctic bottom water, in that we get these water masses with their specific properties entering the high latitudes, where they can be modified by numerous processes and eventually form the very, very dense water that can create the abyssal layer of the ocean. So we can get back to that in a little bit, but again, let's ask ourselves what might be the effect if we lost this sort of core one and we lost this warm inflow into the Weddell gyre. if you recall that other than the warm inflow in the interior of the Weddell Gyre, we have what's called the cold regime, where sort of Weddell Gyre interior waters just recirculate. And if that were to sort of lose its input of warm water, then the already high density region of the gyre interior, which is, part of this circulation of the gyre with the ASC and the ACC on its southern and northern flanks, we'd get this density increasing, and we'd have a higher gradient between the sort of shelf waters where the Antarctic slope current is flowing and the gyre interior, which is exactly what we see. And so with that higher density gradient, we also see an intensification of the Antarctic slope current in terms of mean kinetic energy here. And as we know from barotropic eddy generation and baroclinic, frankly, with the density gradient, we get an intensification of the eddy activity along the Antarctic slope current. And interestingly, this is one of the ways in which water, and particularly heat, crosses the Antarctic shelf break through the stirring of the eddy activity in the Antarctic slope current. We also see, historically where we had the ASC turn south, you had some eddy activity breaking off of it and entering the gyre interior, and it seems like the ASC with that higher density gradient is sticking more firmly to the shelf break, and we get this region of eddy activity declining. I think that's all I'll go over in terms of the spatial change, and I am aware of the time, so I'll try to finish up quickly. The next thing that I wanted to get into was the sort of 3D structure and the seasonal cycle of eddy activity. And here the dominant feature, I think, is the sea ice. This is fairly well understood from studies of the Arctic. Basically, sea ice acts as a friction over the ocean surface and can dampen eddy activity. So this makes sense in two ways. One, we have the seasonal cycle of eddy activity, which is very clear in the seasonal cycle of sea ice, which is very clear in our eddy population, damping eddy activity when sea ice is high. And we also see it in the sort of 3D structure where at the surface, you actually don't have your peak of eddy activity because you have the most damping from sea ice, but we rather find a peak at depth. And of course, in the context of climate change, this is expected to decline as sea ice declines. And we also have a decline in the seasonal cycle because we can't reduce our sea ice past 0% coverage. So we have more of an increase during the winter months than in the summer. So we have this seasonal cycle in the population, which I think is pretty straightforward, but we also have a seasonal cycle in the proportion of cyclones to anticyclones. So as it turns out, it seems that sea ice disproportionately kills cyclonic eddies rather than anticyclones. Again, this is something that's been observed in the Arctic, primarily through in situ observations using ice-tethered profilers. And I think that's important because essentially what they do is they find multi-year ice that they expect to last more than one season, and they use that as an observation platform. And so given that we have a strong seasonal cycle, and the other thing from the Arctic is that they find a much stronger dominance of anticyclones. So there are some studies that have something like 90% of the eddies observed being anticyclones. Or anticyclonic. And I think given that we have this seasonal cycle and we only have something like, a 10% difference in cyclonic and anticyclonic eddies, we might ask ourselves, well, one, what could the differences be? One difference is that the Arctic keeps more of its sea ice in the summer than the southern hemisphere. But the other is probably that the observation platform of thick multi-year ice is sort of giving you a certain view of the Arctic Ocean, which may not be so reflective of the seasonally sea ice covered area, which is probably more of what we're seeing in the southern hemisphere. So I don't think that these two things are sort of at odds with one another, but I think it does really paint a clearer picture of the impacts of sea ice on cyclone or anticyclone proportion, given that you have a very limited set of observations in the Arctic and from a specific observation platform, essentially. In terms of why this might be, there's, I don't think, a consensus on why this happens, but there are some theories that say, for example, eddies can be generated in pairs, with cyclones tending to be at lower, shallower depths than the anticyclones, which would expose them to more sea ice damping. But that's by no means, I think, a fact. It's rather a hypothesis. And then finally, you may again be asking yourself, okay, the seasonal cycle is quite clear, but what is the relevance to the climate system here? And I think this is really interesting in that cyclones and anticyclones tend to have opposite thermohaline characteristics. And so if we have a selective dampening of one or the other, then that could determine whether under sea ice, eddies can introduce warm anomalies or cold anomalies, or at least tend to introduce warm anomalies or cold anomalies, for example, to the marine terminating land ice. So now I'm going to try to conclude, sum things up, and as well bring back the sort of motivations that we had, because I think actually what this study has done is raise more questions than answers, but really I think it can give us some interesting opportunities for future work. But so first of all, I started with the sort of baseline of how we can understand Southern Ocean eddy activity from Ivy Frendler, and we've been able to add the high latitudes to this from the model data. And I think these figures match up really well, maybe quite conveniently, but I think this is a really satisfying result here. We also were able to go beyond just saying, okay, this is what the model tells us and we can believe it, and rather we're able to relate all of the, or I would say most or all of the eddy activity that we see to well understood regional circulation features. We're also able to make projections in the context of climate change, which I think is still something that's relatively new in terms of model capability, and again related that to more well understood impacts on large-scale circulation features. And finally, we were able to go beyond what typical studies can do using things like observations of sea surface height, in that we were able to look at the sort of three-dimensional structure of eddy activity. But before I finish up, I think there's some really interesting avenues for future work, and I'll try to limit it to my sort of motivations at the beginning. So one, we have this evidence that eddy activity is responsible for a lot of the transport of warm water, essentially heat, towards the Antarctic continent. And one thing that we didn't do was a direct quantification of that heat transport. And I can tell you that we didn't do it because I didn't save daily three-dimensional temperature data due to the size, but that I think is something that really needs to be done in the future. And I think we do have evidence, particularly with the intensification of eddy activity along the Antarctic slope current, that could intensify. But we also have some other interesting caveats in that you may have differences in anticyclonic or cyclonic eddies, or you may have differences in terms of whether the eddy activity in this region is primarily going to break down or transport heat through mixing or through stirring or through trapping, for example. So there's a lot that can be done there. We also have this idea that eddy activity is a component of the production of Antarctic bottom water and overturning circulation. And then we have this really interesting result in that sort of the warm inflow to the Weddell Gyre, so the introduction of precursors to Antarctic bottom water seems to be shifting in the context of climate change. And so I think it would be really interesting to quantify the production of Antarctic bottom water, and then to look at the impacts of eddy activity in modifying the warm deep water that's introduced. And finally, we had this idea that eddies can affect sea ice melt by disturbing insulating meltwater layers. But rather what we found is that sea ice has a clear and dominant impact on the eddy population. But despite this sort of theoretical relationship where eddies can impact the sea ice in return, that's not really something that is clear from this data. So I think more could really be done to look into a two-way relationship there. So that's all I have. I hope we have some time for questions.
Thank you, Nathan. Is there anyone that wants to start with the questions for Nathan? We have like 10, 15 minutes. Steffi, please go ahead.
You might need to unmute yourself.
Let's see, Steffi, is it? Yeah, I see you took your hand down. Okay, maybe while everyone decides to shoot or not, I want to ask you, did you notice any big differences compared to the reference medium resolution experiments in the Southern Ocean?
So in the lower latitudes, the first paper, the one that I mentioned, was really looking into that. The CMIP data was really not able to resolve any eddy activity in the high latitudes, so I didn't really look into that. In the lower latitudes, we found pretty good agreement, I would say. So the spatial patterns of the changes are in very good agreement. And in terms of the magnitude of change, one of the big differences is, of course, with the higher resolution you get, you start to really match the observed magnitudes of eddy activity. So that's, of course, different, but sort of in a good way, I'd say.
And beyond the eddy activity, like the big biases that typically affect the Southern Ocean, did you see clear improvement when you were including the eddies?
So given that we have this sort of medium resolution transient simulation and then the very short time slices of the high resolution simulations, first of all, we don't really expect the deep ocean to be much different at all. It's initialized from the low resolution or the medium resolution simulations. And then even after 6 years of high resolution data, we weren't really expecting to try to get improvements in the sort of climate that we had. Rather, it was more to say that we can investigate the very quick to equilibrate processes like mesoscale eddy activity, but probably the things like temperature and salinity are going to be, first of all, biased mainly based on what the medium resolution run did, and then probably having this sort of initialization shock and drift. And so it wasn't really something that I think this simulation is designed to get right.
Yeah, that's right. I had actually missed that. It's not the right protocol to address the impact on that.
I would say, yeah.
Okay, I see Aaron has his hand up. Please go ahead.
So with kind of how you had the simulation set up, did you have the eddy parameterization in the medium resolution turned on, and then you flipped that off as your eddy permitting, and then once you became eddy resolving, you turned off the mesoscale parameterization, or how did you kind of ensure that you don't have this shock that you're probably still riding the wave of for 5 years?
Yeah, so in the lower resolution simulations, it's a scaled Ghent-Williams. So depending on resolution, you have eddy parameterization, and then yeah, in the high resolution simulations, it's just turned off. So in terms of the shock, I mean, there was a shock for sure, and that's sort of what we deal with, what we put up with to have this sort of eddy resolving assessment of climate change. Yeah, I think it's more just something that you have to accept. Unless you have an idea of how to the shock.
Yeah, I mean, and could you see like how long it took to dissipate? And presumably within those 5 years. So then you took kind of the end of that high resolution period, or how did you try to alleviate it?
I'm not sure what you mean. I mean, the shock, I think, will show itself in terms of the climate sort of adjusting in many ways, and I didn't really produce good assessments of, you know, year by year temperature bias or something like that. So I don't really know how long it took to, or if it's dissipating or getting worse. And I think keeping the time slice simulations relatively short is actually one way to sort of reduce that impact of any drift that you get. And when I did look into things like bias in terms of temperature and salinity, I just used sort of the entire period as a mean to try to, you know, treat these 5 or 6 years as one climate rather than look into any sort of trends or.
Yeah, cool. Thank you.
David, do you have a question? Nathan, maybe can be the last one and then move on to the next.
Yeah. Hi, Nathan. Just real quick, I think you probably said it, but I didn't quite catch it. Could you explain why there's this predominance of, I don't remember, anticyclonic or cyclonic in the Arctic, and the ice plays a major role in one of them only, and there's this asymmetry? Could you maybe say a little bit more about that?
Sure. So first of all, I don't think that there's a real consensus on why sea ice tends to dampen cyclones more than anticyclones. There are some theories, such as, you know, if cyclones are generated more like in a more lower depths, so closer to the surface, which would expose them to more sea ice friction. But I don't think that that's fact. It's a hypothesis. And what the difference between the Arctic and the Antarctic regions might be. First of all, I think it's very difficult to say because there hasn't been a lot of research on this. And in the Arctic, it's been done primarily through in situ measurements from ice tether profilers. In the southern hemisphere, there isn't much ice tether profiler data. And so comparing my results to theirs, I think the methodology could be one of the reasons why. So if you have ice tethered profilers, which are specifically targeting multi-year ice, thick ice that's going to last more than one season so that you can collect more data, then you might, I don't want to say bias the data set because, you know, you are observing what's under that thick ice, and there is that thick ice in the Arctic, but you might be getting a sort of selective view of things. Whereas with the model data, you're really taking the entire region. And so you see more of a seasonal cycle, and you see how when there's ice, you get these effects, and when there's not, things start to go back to normal. And that's also, to add another caveat to that, that's also something that you see more in the southern hemisphere, where the winters were always more sea ice free. So there was less sea ice sustained over summer than in the Arctic. I hope I said that right.